Hi, everybody. Welcome. I hope you have had a good morning so far here at Device Talks Boston. This is our second day of programming, so if you're just joining us, welcome. My name is Sarah Falkner. I'm the program manager for Device Talks, so my job is to find great speakers like Dan. If you're interested in helping to develop some programming with me, get in touch with me. If you're interested in speaking, also get in touch with me. And if you're interested in neither, I'd still love to meet you. So I'll be here all day and I would love to get in touch. So, for this morning's keynote, we have Dan Wetmore. He's the Director of Clinical and Research Partnerships at CTRL-labs, a really exciting company that I'm really thrilled to tell you all a little bit more about today. And Dan's certainly going to show us some interesting things, so I think it's going to be great. Dan, to start, you have an interesting path. You have a PhD in neuroscience. You did some early stage neurotech projects, and eventually you land at CTRL-labs in your current role. Tell me a little bit about how the company itself came to be and what you do in your current role.
Well, first of all, thanks for having me here today. So CTRL-labs was founded in 2015 out of Columbia Neuroscience. And are we on now? Can everyone? Good. Out of Columbia Neuroscience with the vision of creating neural interfaces for universal machine control for 8 billion people, for everybody. So that means consumer applications and clinical applications as well. So that's one of the reasons we're here today. The early path of the company is a little bit interesting. So the two of the founders out of Columbia Neuroscience, Patrick Kaifosh, our CSO, incredible expert in machine learning and computational neuroscience. And another one is Thomas Reardon. And Reardon has a rather unique path. Neuroscience and his PhD was his second career. And earlier he was in software. He worked at Microsoft, was part of the core team that developed the first Internet Explorer. So that puts a timeline on how long he's been at this. It was founded in 2015 in New York, and I joined about 6 months ago. And when I joined, there's kind of 2 or 3 core reasons that I joined. So the first is that I like soccer and played a lot of soccer. The second is I'd been burned a little bit from a startup that launched but hadn't really validated the technology. And the third is I love New York. So I had been in San Francisco for a long time. I moved out to New York, and it's a relatively small neurotechnology community. And I was quickly introduced to this new company, CTRL-labs. And I looked them up quickly and realized that a soccer buddy from the Lumosity team in San Francisco years and years ago was one of the early employees there, which really brought me in. And I came and looked at technology. I was very compelled and realized it was a little bit too early. So the whole idea was to use electromyography, EMG, as a way to create a neural interface that's universal. And for me, I just didn't see at that point 2 years ago when I first stepped in how far this technology could come. And so I kept in touch with the team, and about 6 or 8 months ago came back in and saw how much progress had been made and realized that the viability was really there. And not only that we had an incredible potential, and we'll talk more about exactly how we do this, to create universal neural interfaces, but that even though the focus of the company for these first years had been on consumer applications, that there's incredible potential that was untapped to help in health and well-being, to work in clinical domains. And so that's one of my focuses, along with engaging with research partners in academia and in private industry.
So I want to dig in a little bit deeper into the technology itself. Tell us a little bit about how the technology works, what it is. Let's give the audience a little sense of what we're talking about here.
Sure. So generally, when most people think about neural interfaces, you think about the brain. But the brain is not our whole nervous system, right? Our nervous system includes our peripheral nervous system as well. And the technology that we've developed leverages some of the form factor benefits and other control benefits of the motor nervous system. So we have built a bracelet that goes on your wrist or forearm and records electromyography, the electrical signals caused by your motor neurons in your spine synapsing onto your muscles and causing those muscle fibers to contract. So the only output of the brain, like all the ideation and thinking and dreams and whatnot, the only way we interact with the world is through our motor nervous system, whether it's shaking a hand or speaking, walking down the street. And this allows us to have very high volitional control and fine control and intuitive control for a neural interface based on the motor nervous system. So our EMG array records the activity in the forearm, and these are the muscles, these 14, and actually some people 15 muscles, control the movements, most of the movements of your fingers, your wrist, your hand. And by recording these signals and leveraging a team of dozens of machine learning, computational neuroscience experts, we can infer in real time what the position and forces of your hand and fingers. So as you might imagine, this now enables us to create virtual controls where before you might have needed a transducer. So a simple way to think about this, when we interact with machines, we generally do so by generating a command, a motor command, and then our musculoskeletal system transduces that into some movement or speech, and then there's a sensor. A sensor could be a microphone, a sensor could be a keyboard or a smartphone, and then that controls the machines. But wouldn't it be a little lower friction and more beneficial to go directly from the motor activity that we can record from your forearm to machine control? And so the idea is that if we create a system that goes directly from your motor control to machine control, this is the basis for a much more general and scalable neural interface.
So you're kind of answering this question, but you have said to me, and your company kind of believes that, and I want to get this exactly right, quote, non-invasive neural interfaces are the inevitable solution for the input and output problems of today. What does that mean?
So you got it right. You're on brand already. Thank you. So generally, our sensory systems, vision, touch, hearing, have a bandwidth that is many, many orders of magnitude larger than our output. So there's this mismatch, right? So we have input that can look at 10 screens at once, that can listen to a conversation with someone we're talking to in a crowded room with a lot of background. We have an incredible amount of sensory information that can come in, but we're limited because the output, it's only through our motor nervous system, and traditionally the amount of information that we can transduce, either through speech or writing on a computer or in other means, is far more limited. So as machines become more and more integrated into our daily life, what are some of the tools that will overcome that mismatch? It's a fundamental problem that spans across domains in the consumer and clinical space. How do we overcome this? And so for us, the thinking is that if we can create tools and systems and platforms that in many form factors, integrated with many types of technology, can overcome this mismatch, we can enable our output to scale up considerably, similar to what we can do with our inputs naturally.
So to help drive this home, you've brought some really cool videos that you want to share. Do you want to dive right into them?
Yeah, so I will give a little bit of background about the videos, and then we'll dive in. It's definitely a seeing is believing kind of state of things. So we have developed a series of, we have a hardware team. Our hardware team develops the most amazing dry electrode, multi-channel EMG systems. We work with the best EMG labs, and they usually, historically, have used systems that are tabletop systems and require abrading the skin and whatnot. We have a bracelet. You'll see in the videos two versions of our bracelet. Our most recent one is a single integrated form factor. You'll also see one that has two little wristbands. That's an earlier version. And what it does is it records the EMG, it sends it wirelessly to a computer that runs our software and allows us to enable different immersive experiences or control experiences. You ready? Okay. So the first video shows hand state. So what you're looking at on, I think this is Reardon's arm. He is recording activity from the muscles in his wrist, and in real time, our system is rendering those on a virtual hand. And what's incredible about this is a generalized model. This is a model that we've developed from training data built from hundreds and hundreds of individuals that works really well, really quite well for anyone who just slips on the system. And all of a sudden, if he can reliably move his thumb in that way, all of a sudden that's a button, as an example, let alone the immersive potential in virtual or augmented reality. But we're not just about that, we're also about your intention. What is your intention in a control scheme? So in this video, also showing a similar rendering, but in this case, he tries to extend his hand, and he's flexing the muscles that would do so, but holding the fingers and not allowing them to extend. And by doing so, that shows an example of how we can use your intention, not just your movements, as a way to improve control. We have a little bit of sense of humor. So this is my colleague Adam controlling a robot through a set of mappings from his muscle activity in his arm and his gestures to the control scheme of the robot. Now, you know, it's nice to have something like this available when you've got an itch you can't reach. But I think the important lesson to take away here is that not only can we develop control for a virtual hand that has 5 fingers, our motor nervous system is highly flexible, right? Each of us recognize this. We use tools. We play instruments. These are physical manifestations that allow us to do different things in the world with our motor nervous system that don't necessarily map onto our existing anatomy. And so Adam controlling the robot to give himself a scratch on the back is an example of how we can create even more diverse and sort of magical types of control. So this is one of our latest videos that I'm actually going to show twice because there's a lot going on here. This is a little virtual world that our team built. It's not official, but I call it Back to the Fuchsia. And what you see on the right is my colleague wearing one of our most recent hardware. And in this video, I'll start it up here, you've got an incredible amount of functionality to interact at a distance and virtually with control. So he uses one gesture to grab an object. He uses a fist to bring it closer. He uses different pinches of mitten fingers to your thumb to spin in different directions. And what you might notice is the spin is not necessarily at a fixed speed because we can map the force that you're generating from those gestures. And what he's doing now is he's throwing balls out into the environment, and he's doing so through a custom gesture of a little, shooting gesture that we trained up just for him, and something that can be done on the order of tens of seconds. I'm going to play it one more time because there's a couple things you might have missed. So first of all, picking up the device and we have an IMU on board that allows further interactions and movements. You'll notice that he's spinning the device, the block in several dimensions by pinching different fingers. And then he opens his hand and pushes it away, knocking into something else. He's now going to flick little balls into the environment using that gesture. And at the end, to reset it, he's going to give it a snap. And it resets it. And so that snap is, again, something that we can easily train up to allow you to have some nice control. But there's a lot more we can do with this. So if you can have a button virtually, why can't you have a keyboard on any surface? So in this video, there's a band on each arm, and we've trained up some special models, a lot of effort going into this at the company right now, that allows one to type on the table. When you can type on the table, that allows just a totally new set of interactions with technology in your environment. What's more is we can add different gestures to that typing that wouldn't be possible on a natural keyboard. You can make it go away with one gesture. You can do another gesture if you want to do a function key or a caps lock or even more so. So the typing is an incredible achievement. This is the type of thing that we are moving very quickly on the order of weeks and months, make huge advances on this, but it's really something that's never been done before. This video is about what we call neurocontrol. So generally, when you do a gross movement of your hand, you're causing many hundreds or even thousands of motor neurons in your spinal cord to activate the muscles that cause those movements. But it turns out that humans can also volitionally control a single motor neuron. So that motor unit is a signal that we can record from our device. And if you can record reliably a single motor unit, let's make it into a button. And so what we've done here is train up the world's perfect button without false positives or false negatives. He's activating in his right arm without moving, but he can also move and not activate it. What's more, he comes back to activating here. He can pick up an object, and we've thought about hands-free control, but what about hands-full control? What if you're in an industrial environment or an astronaut on a spacewalk? You might need to have controls even when your hands are full of something else. So this is another just incredible achievement from the technical team, that he can even write a message which requires basically all of the muscles of your forearm to be active without making the button go. A little cheeky, no false positives. Okay, last video. And this is, I think, a good transition to begin thinking about what can we do in the clinical domain with the technology we're developing. So what you'll see at the beginning of the video, again, a virtual hand rendering in real time from our system. And this is actually one of our scientific advisors, Greg Wayne, who is a researcher at DeepMind, part of Google. But the difference is Greg was born without a typical hand. He's never controlled a 5-finger hand before, but he has muscles that can do so. And in a matter of minutes, he negotiates with the models and quickly learns how to control this virtual hand. And not only that is the green bar will show the amount of force that he's exerting in a fist pose that he can't actually make in a typical way. And so for us, I mean, this is kind of a magical video and gives a hint of what we might be able to do for people like Greg and many others in the accessibility domain.
Yeah, the videos are really cool. I think they really do speak for themselves. You're right, we kind of beautifully transitioned into our next little discussion point here, but tell us a little bit about what your team envisions the clinical applications being for this kind of a technology, because it's obviously amazing to create games and things to scratch your back and stuff like that, but you've also talked about maybe the more obvious clinical applications and then the non-traditional ones that maybe you wouldn't envision for a technology like this. So share with the audience a little bit about what your company's envisioning.
Yeah, it's a great topic. And to be honest, one of the reasons I want to engage with many of you to help identify the right ways to get our technology in the clinical arena. So there's a number of categories. So at a very high level, let's think of 2 big categories. One category uses either hand state or some of these control schemes in the clinical domain. The other category uses the raw EMG signals or some processed and analyzed version of those signals in a clinical domain. So what are some of the examples here? So a first example is to integrate our system in VR experiences. So phantom limb pain, individuals often use mirror therapy, and people have begun to use VR as a more immersive form of mirror therapy. That's an obvious fit for our technology because the residuum of the patient with the hand amputation may be sufficient to still control that hand rather than doing mirror therapy with the other hand. There's another category, intraoperative monitoring and surgical robotics. We've had a lot of interest there because we have the potential to span across the sterile field, where a device can be worn under a gown and still used to control non-sterile equipment in the OR. Another category that's obvious, perhaps, is prosthetic control. So we're working with some of the best groups in the world to build new forms of myocontrol for prosthetics. It's actually pretty remarkable to me how big the mismatch is between the quality of the electromechanical systems that have been developed in the last 5 to 10 years for prosthetics and the control schemes. So for instance, DECA nearby here has developed with a lot of DARPA money an arm prosthetic system called the Luke system. And unfortunately, many of the people who have the Luke system use a foot pedal, essentially, an IMU, an accelerometer on their foot to control the prosthetic. We can do a lot better with biomimetic and natural controls and enable patients to leverage those developments more effectively. There's another big category in rehabilitation. So individuals who have had a stroke or a spinal cord injury generally are able to move or to activate single motor units or a small amount of activity in their affected limb, but without feedback, without some system that identifies that activation and feedback that allows them in a therapeutic setting to continue to improve that activation and gain functionality, there's a lot of limitations. So we're working closely with groups at Hopkins and elsewhere in neurorehabilitation. The last one, I think, is the largest potential opportunity and one where we really want to work with stakeholders across the clinical domains to find the right fit. So EMG is, like I said, the only output of your nervous system. And so it's been largely neglected. It's not sexy, I guess, as EEG, brain recordings, but it should be. And the reality is, if we can record signals from patients that correspond to the function of their nervous system, their brain and their peripheral nervous system, we have the potential to have diagnostics and biomarkers for a range of disorders. So this is obvious perhaps for motor disorders. So for example, in Parkinson's, can we help a clinician program a deep brain implant more effectively? Can we have scales that are more objective than the standard clinical rating scales? Even outside of motor disorders and neuropathies, mood disorders, psychiatric disorders like schizophrenia, there's been a lot of work recently identifying that there are some clues in terms of motor output. Generally, it's been with gait, but people have looked at other forms of motor output that indicate the function, the status of those diseases. Those will take a little longer to develop, but we are actively partnering with labs and companies to develop early data sets to support that.
It strikes me as you talk about all these potential clinical applications. It's such a wide array. How do you, tasked in your current role, how do you pick partners? How do you guys pick which clinical path to pursue, which to hold off on? How do you prioritize?
So we take a couple filters on that. One filter is how good is the fit right now for having impact. Prosthetics is a good example. Another filter is how big of an impact can we have. Right? Prosthetics is a little bit different there because it tends to be a smaller set of people, but stroke affects a really large population of individuals is an area we can have big impact. And the third category, or the third criterion we use is how can we do something that's different and special and a 10x improvement instead of just an incremental improvement. And I think that's some of those longer term impacts that we can have. Can we help in the diagnosis of differential diagnosis of early neurodegenerative processes? Maybe in the future. That's something that we would love to explore. So for us, it's what impact can we have early, and we're engaging with some of those. And also, who are the outside partners that we can work with? We are a developer and partner-focused company. Our business model is not necessarily to bring products to market, although we are positioned to do so, but we want to enable others to come up with amazing discoveries based on the foundations that we've built and allow, in partnership, these technologies to reach a much larger population.
So shifting gears just a little bit here, where does your own interest in neuroscience come from? I have friends and family members who have undergone the PhD process. It is not something you should take lightly. So where does your own interest in that field come from?
Undergone is a good word. 6 years in a basement. Yeah. So, I became interested in neuroscience in undergrad. I went to Columbia. My dad said, my only requirement is you take one econ class. And I did that. I actually did the whole major. But once I checked that box relatively early, I wanted to explore other things of interest, and biology had always been one. But I hadn't really explored neuroscience, and I took an intro neuroscience class with Darcy Kelly at Columbia, who's just a great, energetic teacher, and it was just a wow aha moment. And it just resonated with me, and we're all we are neuroscience, right? So for me, that made a lot of sense. And then I had to choose between these two interests, and it was either going to be stay in New York and be a banker. But I, even though I'm wearing a coat today because we're in a clinical audience, I guess I put the startup hoodie aside. That just wasn't a good fit for me. So I followed my now wife to Cambridge, England, where she had a Fulbright and joined a lab there. It was doing motor neuroscience, and then we were recording cells in the motor nervous system, and you could hear the pop of each cell every time a certain movement happened. That was amazing. So that's when I decided this is the first job I've ever had that I didn't hate. That's probably a good sign. I should do more of this. And that was the inspiration to say, okay, I'm going to go get a PhD. So went to Stanford, joined a lab that is very multidisciplinary with Mark Schnitzer. And we had physicists and engineers and mechanical engineers, and we built microscopes. And I studied the cerebellum, again, part of the motor nervous system. And, to be honest, was just inspired by what we could learn about neuroscience. The lab work was hard, and I obviously didn't stay in academia because for me that just didn't seem like a way that I personally could have a big impact.
In the medical device industry, we're having these conversations about how to engage with big tech players as they come into the space, as they make their way into the medical device industry. How do we, work with patient groups because the medical device industry is becoming more consumer focused? That's great. When you look around the industry, whether it's tech or a straight medical device, what kind of technology is exciting to you?
Yeah, for me, there's a couple of things that I look for in exciting new technology. Some are, I think, kind of unique to my personal interests, and some have to do with what are the criteria that you use to evaluate whether this can have an impact and go all the way. So for me personally, I've always been interested in multidisciplinary projects. I've done projects that span from nanotech to life science, to molecular biology. I've done, that interface between hardware and biology is very interesting, and it also requires a lot of disciplines because the human factors really, really matter. Not just what is it like to interact with this device or wear this system, what does it look like on you, right? I was part of a company, Think, that had a device that you wore on your face, and turns out you're only supposed to put glasses on your face. At least, I don't know, maybe things will change with our AR, VR future. So multidisciplinary is a big one for me. And the second is something that is, I generally can't help myself but to be drawn to things that are a little bit counterculture in terms of the zeitgeist of a particular field of science. Those are interesting to me because they have the potential to be that 10x shift, not just an incremental change in how things are done, but like a transformative impact. And so, a couple of examples of things that I've done in the past that fit that, we incubated a therapeutic program at Stanford after my PhD for intellectual disability and Down syndrome. And at the time, most people thought that you could not treat adults with a neurodevelopmental disorder to improve their intellectual function, that it was all a developmental disorder. Turns out that's wrong, and a lot of companies continue to work in autism and other areas on that. But that miss by the field was really interesting to me. A second one, I've done a lot of work in the peripheral nervous system and neuromodulation, both with electrical stimulation and also ultrasound. And this is one of these areas where in the last few years, there's been a major shift where people recognize that the peripheral nervous system is an area where you can have big impact on disorders that affect one's central nervous system. So one example is Kala Health. Many people may have heard of Kala. They just raised another round. They developed a median nerve stimulator to treat essential tremor that you wear for a few minutes, but has effects that impact the function in the central nervous system that are long-lasting. So for me, those are examples. I think we can't help but, you can't forget, machine learning, AI is the term of art, I guess, generally, but really machine learning is the impactful technology, is positioned to be highly transformative. But that one's really interesting to me, And to be honest, one of the great parts of being at Control Labs, where I get to learn about how machine learning models are effectively implemented, is that having the right question to ask, the right data set to build your models based upon, the right validation framework to determine whether you've really identified something informative versus epiphenomenal, are not trivial. And so the potential impact of machine learning is huge. For me, it's of great interest because it's not as easy as one might think it is to just run some of these, get a big data set and run it through these magic models and the answer comes out. In some cases it is, but in many others it isn't. So for me, that's another interesting one because it requires that scientific method in terms of evaluating and building those frameworks.
You were mentioning kind of trying to think a little bit counter to what the narrative might be in a given field. How do you effectively evaluate that? How do you, when everyone in the field is pointed in one direction, there's of course the risk that you'll turn around and go in the other direction and they will all be correct and you will be wrong, right? So, I mean, how do you make that choice cleanly?
I read the papers, right? I mean, I go back to the data, right? And to be honest, I personally, maybe it's just a personality trait. I have never felt that just because someone has been in a field for a really long time doesn't mean they're right. It means they know a lot. It means they have like a really dense network of people who can help you identify the right questions to ask or find data sets you didn't know about. But I've never felt, maybe it's just a cultural thing. I don't know. I've never felt like just because this is the way things are done means they're right. And so for me, diving into the primary literature and reading it for myself, right? You have to, the discussion section of a scientific paper is, those are opinions largely, right? When you're going into review for an academic paper, that's where the battles are. The battles are in your interpretation generally of the data, not in what the data show themselves. So for me, I've always dived into those and just come up with my own independent opinion, right? And look, it takes a long time for opinions to shift in scientific fields. It's a huge challenge, and there's some systemic reasons for that. Academic groups, people are running small businesses. These are challenging, right? You have to fund the small business with grants. If you're getting all the grants based on hypothesis A, even if you think it might be questionable or wrong, it's really hard. I mean, there's just human beings and people working in your lab and your career and your belief and your ego a little bit probably that make it hard to shift. The system also is in science and clinical science as well, is different than tech, right? Different than, you can have a 23-year-old founder of, or younger of something like Facebook, right? That's not likely to happen very often in clinical settings. So what, the young people who really push forward in research tend to be those developing new tools rather than people who are trying to overcome like a zeitgeist about a field. So, in biology, optogenetics and CRISPR, right? These are two tools that were developed. There's not much controversy there, right? They just work. So that's the reason why tools end up being, I think, a way for a lot of the young people in science to get enough stature to start pushing back on the zeitgeist on those things.
It's interesting. Let's get back to Control Labs briefly. Tell us a little bit about what's on the immediate horizon for you guys.
So we are currently shipping or sampling to developers our units. So we have labs working in research settings and companies that we're working with, both across consumer and clinical, independent developers developing new new applications and games and other environments. And so that will be scaling up over the course of the year. And I encourage all of you, if you have an application you think would be a good fit for what we're doing, let's talk. We want to get systems in your hands to do something really incredible. In-house, the pace of improvements in terms of control and rendering and things like that are really, really fast. So because we've built this amazing hardware, which is always slow, and we're just iterating on the data that's coming through, we can build something incredible like the typing in months, not years, right? And so one of the things that will be a big focus of the next 6 to 12 months, the models will become personalized. So they're not just a general model, but as you use the system more, it learns you. And in fact, we can even detect your neuromuscular fingerprint, right? We're each unique in that way, and allow a lot of these personalizations of how you want to interact with machines to be really reliable, but also fit your preferences, your workflows, whether you want to snap or flick or tap.
It's really very remarkable stuff. I want to turn now to the audience. Does anyone have a question for Dan? I can get a microphone over to you. We've got one up front.
I think all this is fascinating. So super excited to see all the videos that you brought with. And you have your bracelet interface right now. Are you working on other parts of the body to detect those motor signals and be able to translate that into other control devices?
So great question, right? We can control different parts of our body, and EMG can be detected there for other control schemes. We've focused on the forearm for just the natural reason that in your motor cortex, your ability to execute fine control over your hands and fingers is much better than other parts of your body. But we get questions about that regularly, right? If someone's looking at gait or someone wants to develop a lower limb prosthetic, can we use those signals? So to be honest, a lot of the limitation there is form factor. We've built something that fits on the forearm, but to be honest, that is not a long-term limitation. The pipelines and insights about how you take these raw signals and process them in a way that's actionable for machines is not limited to the forearm. So we'll absolutely look to expand elsewhere. And in fact, we have some collaborations right now that are looking at the upper arm for various reasons.
Thanks, Dan. Incredible examples across the board on the technology and innovation. I'm curious to know how Control Labs, you and people on the team, kind of look at these different applications, because, again, outside looking in, every one is a N of one, but yet there's a subset of patients. But as you look at, I guess, just focus on peripheral applications currently, how are you looking at different patient segments, different applications, just from a perspective on the clinical opportunity, kind of the condition evidence, other parts that kind of characterize why a specific application is more attractive than another, because the work that you're doing could be applied, humbly to thousands of different types, but how do you kind of prioritize or look at them internally to say, this is our top 3, top 5, top 10 applications?
Yeah, it's a great question. I can confidently say that I don't have the full answer to that yet. We have a relatively small team looking at clinical applications. Overall, we're about 65 people. So we're a decent size, but we could have 65 people just looking at clinical opportunities, probably. So the best ways to start quickly are to find groups that are familiar with working with EMG. So that's a good first place to start, and have some technical capacity to work with a developer kit rather than something that's intended for a final consumer. We certainly are engaging with people locally in New York and in Boston. Geographic proximity is helpful, but it's not the end all. And then we're trying to balance between some of these different domains, because we want to get far enough into working with, talking to KOLs and getting some proof of concept data to understand where the strengths and weaknesses are of our technology. So we're working with some prosthetics groups, some neurorehabilitation groups, and the area that will be expanding significantly over the next months is to start collecting more ambulatory EMG data from specific patient populations. And that might be it'll certainly be some, neuropathies or motor things that affect the motor system predominantly. One key need, for instance, in MS is to understand the profile of a relapse, right? Clinicians don't have sufficiently good tools to get feedback from their patients about like the duration and severity of a relapse. And there's something specific and actionable there, which is another important filter, right? When I have conversations with KOLs, great, okay, I understand the problem you're trying to address. If you had an answer based on using our system, what would you do differently? And if the answer is I don't know yet, realistically, that's something that's probably a little farther out in terms of where our focus will be. But if the answer is specifically, oh, well, if I had that information, I would have the patient come in, in the next week, and I'd shift their drug regimen because I know that if the relapse is sufficiently bad in MS, then they'll never regain back to a certain level of function. That's really encouraging to us to hear that when we're talking with people. And so, we're to be honest, we've been a little bit hardware limited because of the demand, but that is something that's resolving, and we'll be collecting a lot more data.
Hi, and I'm curious whether you can control this movement also with this EEG brainwave.
Yeah, so good question. So many people, many groups work with EEG, right? So non-invasive recordings of brain potentials. Personally, and definitely personal opinion, but also the opinion of control labs, is that those signals are less useful for control for a couple reasons. So one reason is that you volitionally control your muscles. That's natural, right? A small child does that without any training. But to volitionally control your brain rhythms in a low latency, reliable control scheme is somewhere between impossible or requiring a lot of training, right? The signals that we're recording are causing the actual volitional interaction with the world. They're causing the movements. Whereas with EEG, you're kind of listening in from outside the stadium, and it's a little epiphenomenal, right? The brain did not evolve so that we could record, potentials combined, averaged across hundreds of thousands of neurons to make a control scheme. So even though it seems like, oh, let's go straight to the brain to get these signals, I don't think EEG is the right way. And I'd actually push back, and we talked about this a little bit earlier. You've probably seen some press article about someone who controlled a drone with their mind, perhaps, right? They used EEG to control a drone. And for me, that sort of headline makes me cringe. I would ask that we try to avoid that type of headline. First of all, when you were controlling the drone with a joystick, you were still using your mind, right? The point is that I think what they're trying to say is the drone is being controlled through EEG activity. But that's just not a very sensitive, reliable, scalable form of neural interface.
Got another question up.
I'm not sure I could, very nice presentation. I'm not sure I can frame this question clearly, but I was recently speaking to people who are involved with brain control interface, and I understood that, so I have limited knowledge of it, but I understood that at University of Toronto, for example, there's a rehabilitation hospital that's experimenting with that, and other people are talking to them about its potential. If I understand what you're saying correctly, if you were to compare what you're doing on a parallel path to brain control interface, which I believe is maybe it's a leap to say it might be better known, but the drawbacks that you identified for BCI are actually very well known, because the EEG signal has lots of problems coming through the brain barrier. So it seems like you potentially are exponentially more advantageous if you're talking about, and I don't know how it would be applied, and I don't know how you'd even compare the signals, but it seems like it would be better what you were doing if you wanted to help these disabled children, for example, control movements not with BCI but with your alternative pathway. And so I just wondered if I've got this correctly, because there's a lot of people also using it in meditation, very widely criticized by the experts using EEG. I mean, I've talked to neuroscientists that hate Muse. They say they're lying and that the engineers know they're lying, and they've sold it to millions of people, and it's not right. And I don't know if you're actually a substitute for that potentially or not.
So thank you for your question. There's a little bit to unpack there. So first, let's talk about BCIs a little bit. So first of all, yes, I agree. I think having a wristband that enables accessibility controls is a much more scalable, safe, inexpensive type of neural interface for many individuals or patients than an implanted brain control interface. But at the same time, I mean, we come from, one of our scientific advisors is Krishna Shenoy. I worked in his lab briefly at Stanford. He's one of the world experts on implanted BCIs. So that field resonates with us. We come from that field in some respect, and there are patients who will need that type of intervention to regain functionality, but it won't be for all of us. And so, you may have heard of companies like Neuralink, which is an Elon Musk company, or Kernel, which Brian Johnson founded. These are generally focused, at least publicly, in terms of their long-term vision, on implantable systems. And if you talk to neurosurgeons about brain implants, they'll generally always tell you it's no big deal. Right? It's what they do every day. But it is a big deal, right? Opening up a skull and putting an electrode is hugely impactful for certain patients, but wouldn't do it at scale. So I think non-invasive is important. And look, we believe, and I think we're showing, that the motor nervous system is the right way to access signals from the nervous system rather than through EEG. We can talk about Muse in the happy hour, perhaps. They have certainly launched to a lot of people, and we know them well.
We've got time for just one more question, so.
Thank you, Don, for presenting about Control Labs. It's a really exciting company. My question is about what sort of avenues would you and Control Labs take in order to break through to more traditional companies that are larger scale and have been in the business for a long time?
So when you see, what type of company do you mean? You mean in the clinical domain or in the consumer space?
In the consumer space.
We don't speak publicly about these, but we can tell you that large consumer companies and companies in the consumer space across a range of sizes and interests are highly engaged, thinking about the next forms. What does that next computing revolution look like? What are the right ways, most effective ways to control it? So for us, in terms of how have we engaged, to be honest, we develop really compelling technology that works, and we create awesome videos to show everyone.
That's true. Okay, thank you.
Great. Dan, thank you so much for joining us today, and thanks to you guys for being here. Let's give Dan a warm round of applause.
Thank you.